female in the population emerges 3 weeks earlier than the latest female in the population. The other thing that you're going to see is the black distribution of the relationship between mating date and emergence date is shown by comparing individual specific emergence dates to mating dates. Each one of these is a data point for a squirrel across the years, and it shows traits again. Assuming that selection is acting on reproductive phenology, so the females are trying to time their reproduction to act or to hit one of those resource peaks, for that selection to invoke an evolutionary response on another trait, the two things need to be genetically correlated. Essentially what I did is partition the phenotypic variation into the underlying genetic and environmental components. The same sort of nature-nurture environment or argument. And heritability then is simply the proportion of that phenotypic variation that has an underlying genetic component to it. It's a proportion, so it varies between 0, which means of all that phenotypic variation that we saw when the animals emerged, none of it has an underlying genetic component. It's all environmental or some other source that is giving rise to that source of variation. To 1, all of the phenotypic variation that we're seeing is due to an underlying genetic variation component. So traditionally, the way one would estimate a heritability is to do what we would call a parent-offspring regression. And this has recently been shown to have relatively limited use in wild populations, but I think it's still useful for bringing across the concept of heritability, which can be new to some people. And essentially what it does is it makes kind of intuitive sense, I think. If we compare the phenotypes of our parents to the phenotypes of our offspring, if tall parents or late